In this section, we're going to talk about nonlinear systems of equations. So remember, back to linear, we were looking where two lines potentially intersected, or in the case of three variables, three lines in 3D. What we want to do now is we want to bump this up to nonlinear, okay? So nonlinear means it's not a line. So this could be something like a quadratic equation or a parabola. This could be something dealing with logs. This could be circles, anything of that nature. It is not a straight line. One of the equations could be a line, but the other might not be. So your goal is still to find points that satisfy both of the equations. So you're still looking for intersection points. So just to give you some examples, maybe we have a parabola for one of our equations, and then the other we have a line. It's very possible that there is a single point of intersection. So in this case, we have one solution. Okay. When it was dealing with lines, you only had three possibilities. There was one solution, there was an infinite number because it was exactly the same line, or there's none. Here, you have tons of options because it's possible I could move this line down instead, and then it would never intersect the parabola, so there would be no solution. Or if I keep that parabola in the same spot, but I move that line up, there are two solutions that satisfy both of the equations. Okay. And then realistically, again, it depends on the shape. There could be more than this. So maybe I still have a parabola that's facing upwards, but then my other equation has a parabola that's going sideways. In this case, there are 4 points of intersection. So there would be 4 solutions, okay? So one thing we should get in a habit of is we either want to graph these pictures to know how many solutions there are, or in the case that it's not terrible numbers, go ahead and actually check that they are solutions. So this way you don't end up with anything extraneous, okay? Realistically, there's no one set way to do these. You're going to use the same methods like elimination and substitution, but typically we're going to try to do elimination and get rid of one variable. It just matters what you're given as to what variable you're going to eliminate. So let's try this next equation here, okay? We want to solve this system of equations. And so if I were to go ahead and plot these, I see I have a y squared. That's going to be some kind of parabola. And I have a y, and then my x is just first powers. So this is going to be a line, and this is going to be some kind of parabola. So in this case, I don't want to eliminate the y variables because I don't have the same power in both. So what we're going to do is we're going to try to get rid of x. Now, you absolutely can use elimination, but this one is definitely primed for substitution because I know what x needs to equal, okay? So in here, this x and this x are going to be exactly the same thing, so I'm just going to directly use substitution. Okay. So my x is equal to y squared plus 1, but I also need 2y minus x to equal 0. So replacing in that x is y squared plus 1, we get an equation solely involving y. That we can now solve. Okay. So it is a quadratic. I definitely want to manipulate this around. So distributing out that minus sign, that's 2y minus y squared minus 1 equals 0. And then putting that in the correct order gives us this. You can definitely try to factor this. However, I hate when that leading coefficient is negative, so I'm going to go ahead and change all of the signs. And then from here, now we go ahead and factor it. We need a y and a y. To get to 1, we need a 1 and a 1, and the term in the middle is negative. So I really only have one option, okay? So setting both equal to 0 results in exactly the same thing. My y coordinate has to equal 1, right? So this tells me my y. Now I can use either equation to find x. But again, I like that x is equal to y squared plus 1. So plugging in y, I get my x is equal to 2. So 2, 1 should be my solution. This is what we get, but let's actually check that this works out. Okay, so my system of equations was 2y minus x equals 0, and y squared plus 1 equals x. So replacing y by 1 and x by 2, y by 1, x by 2. This definitely tells me 2 minus 2 is 0, and 1 plus 1 indeed does equal 2. Okay, so this is our good solution. Now, graphically, we want to see, does this make sense too? Again, one of them is a line, one of them is a parabola. So there is that possibility that there is a single intersection. But let's go ahead and graph these to make sure everything is okay. So 2y minus x needs to equal 0. I got to put this in slope-intercept form. So that's 2y equals x, or y equals a half x. And then we have y squared plus 1 equals x. So if you think about if the roles were reversed, y equals x squared plus 1 is a parabola that opens upwards and has been shifted up 1. So flipping those roles, this is a parabola that's going to open in the positive x direction and be moved in the x direction 1. So if I go ahead and graph these, my intersection point, again, I know should be 2, 1. So starting with that parabola, again, if I plug in y equals 0, then my x will equal 1. If I plug in y equals 1, my x will be 2. If I plug in negative 1, it's negative 2. And it's a parabola that opens sideways. Oops. Then my other equation is a line that goes through 0, 0. My slope is 1/2. So I go up 1 over 2, and it goes through this point here. And then I go ahead and connect the dots. So indeed, I have that single point of intersection at 2, 1. Okay. So that is my only solution to this system. So let's try another one. We have x minus 1 squared plus y squared equals 1, and x minus 1 squared plus y squared equals, or y plus 1 squared equals 1. So if you haven't refreshed on circles in a bit, these are definitely going to come back into play. We will likely either have talked about these at the beginning, or I sometimes lump these in with ellipses because we do that there. But these are standard forms for a circle, and you definitely have seen them before. We need the center of each of these circles and the radius to get a picture. So the center is based on what you subtract from x and y. So in this first case, you're subtracting 1 from x, nothing from y. So that center is going to be 1, 0. And the right-hand side is your radius squared, so your radius is 1. For the second equation, it's the opposite of what you're subtracting. So the center is 1, -1. And again, the right-hand side is the radius squared, so your radius is equal to 1. So I'm going to go ahead and graph these two things, and that should give us a good idea as to how many solutions we should get. Again, not going to be perfect because I'm not perfect on this iPad, but that's okay. So our first circle has a center at 1, 0, and it has a radius of 1. So that means I go out 1 in every direction. And then I have a circle through those points. And you can see definitely not super accurate, but that's okay. There's our first circle. Then our second circle's center is at 1, -1, which would be this point here. Again, the center is not a point on the circle though. Then I go 1 in each direction. And I get my second circle. Okay. So again, the center is not an actual point. So when I go through and I'm trying to find those intersection points, I have 1 right here and 1 right here. So there should be 2 solutions. And so I don't have a way to really solve for one variable in terms of the other. However, what I can do, because I don't want to distribute all this out, I see exactly the same expression on both of them. So we can go through and we can eliminate the x minus 1 squared term. Okay. So I'm going to recopy our equations down here to be able to do that. If I want to eliminate, I need the same thing but the opposite sign. So I'm going to go ahead and just take this top equation and times it by -1. And in doing so, that gives me negative x minus 1 squared minus y squared equals -1. And then positive x minus 1 squared plus y plus 1 squared equals 1. So now we can go ahead and we can add these two equations together, and this full thing cancels because they're the same but opposite signs. And what I'm left with is positive y plus 1 squared minus y squared, and then on the right-hand side, I have equals 0. So I need to solve this resulting quadratic. So copy this down here. To solve this, I've got to be able to group like terms, so I got to get rid of my parentheses. So I indeed have to FOIL this thing. My first term is y squared. My outer and inner are the same thing. They're both plus y. So that's plus 2y. And my last term is 1. And then thankfully we have y squared minus y squared. So those are gone. And that leaves us with 2y plus 1 equals 0. So solving for y, we go ahead and subtract 1. Dividing by 2 gives us a y value of -1/2. Okay. And that seemingly makes sense that I have one y value because These look like they have the same y value just because of symmetry. And now from here, I need to find x. And I should get two x values. Okay. So again, you can pick either equation to plug y into. I don't feel like adding that to a fraction, so I'm going to go ahead and use that first equation. X minus 1 squared plus y squared needs to equal 1. So x minus 1 squared plus negative 1/2 squared must equal 1. That gives me plus 1/4. And then moving that 1/4 to the other side gives me x minus 1 squared should equal 3/4. If you really felt like it, you could totally distribute this all out and then move everything back over and use the quadratic equation. But this is pretty much set up to be able to take a square root. So at this point, I'm going to go ahead and take the square root of both sides. But remember, when we do that, we've got to introduce a plus or minus. So the square and square root cancel and give us x minus 1, but that leaves me with plus or minus the square root of 3/4. Okay. And then we can take the square root of each individually. So you get the square root of 3 in the top, and then square root of 4 in the bottom is 2. So solving for x, we just need to add 1 to the other side. And that gives me two different x values. So my solutions are the following. One x value is 1 plus root 3 over 2, with negative 1/2 as the y value. And the second would be 1 minus root 3 over 2, with the same y value. So again, this gave us two separate x values corresponding to y equals 1/2. You could sit there and you could try to check these, but this is what I mean. It's kind of messy. I know there are two solutions, and based on the symmetry, they should have differing x values, but they should have the same y values. So I ended up with two solutions. It seems reasonable from here. Okay. For this next one, the first one is a circle because I've got x squared plus y squared equals 5. The second one we haven't talked about, but it's kind of similar to a circle. So that's actually going to be an ellipse, which just means it's going to be flattened out in a way. Okay. So I want to figure out where these two intersect each other. Right. This one's going to be a little bit weird because you're going to see we end up with something imaginary, but we're still going to have solutions to these equations. They just don't necessarily correspond to an intercept on a graph. So I'll show you with Desmos. We'll go ahead and plot both of these and you'll see they don't intersect. However, there still are values that satisfy both equations. So what I want to do is I want to eliminate one of my variables. So if I make this a -4, then my x's would cancel. Instead, I'm going to make this a -3 and get rid of my y values. So I'm going to take this top equation and times it by -3. So what that gives me is -3x squared minus 3y squared equals -15. And then we did nothing with the second equation. But now we're good. We can go ahead and add these together. And that makes the y squared terms disappear. So -3 plus 4 gives me 1x squared. -15 plus 11 gives me -4. So if I go to solve for x, I've got to take a square root. But again, I get a plus or minus anytime I do that. And the problem is here, I get the square root of -4 underneath. That is not a real number. That is an imaginary number. Remember, that becomes I. So we get two values, x equals 2i and x equals -i. So we're going to have imaginary solutions. And again, it just doesn't correspond to an intercepts. So we ended up with two options, positive 2i and negative 2i. Now I want to see for each of these x values, what does y have to equal? They might be real, they might be imaginary. But we'll start with plugging in 2i for x. And then we'll do the same thing. We'll plug in negative 2i. You can use either equation, but I think the first one's definitely cleaner. So x squared plus y squared needs to equal 5. Well, x is 2i, so we're going to square that. So 2i squared results in 4i squared plus y squared equals 5. And I is the square root of -1, so I squared is -1. So this gives me -4 plus y squared equals 5. Adding the 4 over gives me y squared equals 9. And then when I take a square root, you get two answers, plus or minus 3. So corresponding to 2i, we have the solution positive 3. And then we also have the solution negative 3. Okay. So these are both solutions. Now I want to do exactly the same thing. When x equals negative 2i, we're going to see what does y have to equal. And I'm going to use the same equation. So negative 2i squared plus y squared needs to equal 5. Well, that minus minus cancels and gives us 4i squared plus y squared equals 5. These are exactly the same thing, so there is no reason for me to go through the exact same steps. You end up with y equals plus or minus 3. So we end up with two more solutions, negative 2i positive 3 and negative 2i negative 3. Okay. So I just want to show you with Desmos what these look like. So first, that is a circle, x squared plus y squared equals 5. Is the circle centered at 0, 0. The next one is 4x squared plus 3y squared equals 11. You end up with not a circle, it is an ellipse, it just has a funky shape to it. So there are no intersection points. So there's no real numbers that solve this equation, but there were imaginary solutions to this, okay? So again, the graph is fantastic for us, but since we do know a little bit more about real numbers, and imaginary numbers, we definitely can get some funky solutions now, okay? So every one of these problems is going to be very different. It really is just going to be a matter of which variable can you eliminate or which term can you eliminate and try to solve it from there.